Hello. Okay, these are the chapter 24 homework solutions. We went over some of these in class, and like I said, I think I was kind of disappointed that you have not been working more together on some of these challenging problems. Nonetheless, you need to have these corrected for when we have a test over this stuff. So, in this case, you could use this formula to figure out the field strength at a certain distance from the wire, but since this is twice as far away from the bottom wire as the top wire, conceptually you could probably figure out that that would be 20 amps. But you need to at least explain how you get that. For P13, that was a solenoid, so this is a formula, I think it's on page 895. Formula for solenoid on page 895, I think. And see if we can make that something a little greener like that. Okay. Ugh. Okay. And that lets us, if there's certain turns per meter, the current going through it, multiplied by that vacuum permeability, that helps you figure out the current. That's a lot of current, by the way. For P25, you need to recognize that the magnetic force is going to act as a centripetal force. You also need to know that the mass of a proton, mass of an electron, those are on your formula sheet. So we set the magnetic force equal to the centripetal force, rearrange that, get mv over qb. That's a very common thing for them to ask you, like on an AP exam. So, and that is not a formula on your formula sheet. You need to be able to derive that. And actually, even the centripetal force one isn't on the formula sheet. Centripetal acceleration is, and they would anticipate that you would know that Newton's second law is mass times acceleration, and therefore you could get centripetal force from that. So that's kind of a long stretch. At any rate, the radius of an electron and proton are these two numbers based on a lot of plugging and chugging. For P33, this wire is in this magnetic field. It's levitated, and it indicates that you're asked to find the field strength. Well, if the mass of the wire is 2 grams, gravitational force down is mg, magnetic force up, BIL. So mg comes out to a very small amount, basically 2 times 10 to the negative second, or 0.02 newtons, and that equals B times the current times the length of the wire in the field. And you can also figure out from that if it's conventional current and the force is up, then the magnetic field must point out of the page. For problem 44, we have this area, which is in the magnetic field, field strength of 50 millitesla, or 0.050 Tesla. To find the magnetic force, we need to find the current. Well, that's 15 volts divided by 3 ohms, so that's 5 amps. That's going to be going down the right side. So if conventional current is going down, and the field is into the page, the force is going to be to the right. Now, to figure out how much force that is, we're going to use Fabel, or the force on the wire is equal to magnetic field strength times current times the length of the wire that's in the field, and that gets us 0.025 newtons. Problem 46. We've got an electron going in here at 1 times 10 to the 7th meters per second. This was the toughest problem. I think I told you that I ended up using well over half of a page. I think we went over this in class. And there might have been a couple other ways to do this, a little, slightly fewer steps. But first big thing, recognize the two forces acting on the electron. The gravitational force is, by the way, so small, since the mass of an electron is only 10 to the negative 31st kilograms-ish. That's far smaller than either of these two forces. So, if nothing else, you could have found out that the left-hand rule, since you're using an electron, would indicate that the field is into the page to get us a force that's downward. First thing I would do is find the electric field strength, and then use that to find electric force. So this is a big idea in this. If you don't get that, it's going to be hard to do much else, other than get the direction of the field, and you may be drawing a free body diagram. So then we're going to set the electric field force equal to the magnetic force, and then that's pretty easy to do. So I could say that EQ is equal to QVB. Note the specific amount of charge actually doesn't matter at all here. It's just the field strength since they're both acting on the same charge. 24, or chapter 24, problems 47 and 57. 57 was another one. We dealt with the formula of a solenoid. That's on page, I guess it's page 850. Ooh, I should go back and check. Let me check. Yep, I'll have to go back and fix that other one. So it's on page 850. It said that the ferromagnetic properties of the nail multiplied by the field strength by 100 compared to what it would otherwise be. So basically, this is figuring out the field strength, vacuum permeability, 4 pi times 10 to the negative 7th, turns per meter, and the current. So I'm going to go back and fix this, because it is page 850. Okay, and then going back to 47, 2 springs here, the current's going up, it says the springs are stretched, so that means the springs are pulling to the left, the magnetic force is pulling to the right. If you know that, then you can figure out, I guess you weren't asked the direction of the field because it was given to you or shown as dots, but you could figure out that if the current's going up, that the magnetic force should be, I don't know if that's right or not. I have to think about that. I thought the magnetic force was to the right since the springs were to the left. And if that's true, I don't know if I drew that right. Let me go back again and take a look. So field coming out of the page, yeah, it is. I'm just looking at the handle is correct. So that's correct. Just having to think about the field coming out of the page and the thumb going up. So the force is to the right on the wire from the magnetic field. So the force in the springs is to the left. You probably have to remember this, that Hooke's law, F equals Kx, technically that's absolute value. So 10 newtons per meter stretched by 0.01 meters. But there's 2 springs, each with that spring constant, so it's 0.2 newtons to the left, magnetic force is 0.2 newtons to the right, and therefore we get the current would be 2.0 amps using these, setting these forces as equal. So essentially you have 2K delta X equals BIL. Hopefully you look over those and think about them again, because like I said, I think you want to make sure you understand how to perform some of these things mathematically as well as conceptually. So hopefully that's good, and